Welcome, Wonder Woman of the World. This is Ilona Budapesti, Chief Storyteller of 1 Million Women to Tech, and
this is Frederick Kastad, Chief Mentor of 1 Million Women to Tech,
and
this
we are
is
back with
Winter of Data Hypothesis Testing, Day 2.
Let's get started.
All right.
Daniela, were you able to get the code? I pushed it yesterday.
So yesterday we started looking at a data set that shows grades from the New York State test for girls and boys in grades 3 and 8 in the years 2006 to 2011 in different boroughs in New York City. We saw, well, first we did a bit of pre-processing and organized the data in the so-called pivot table. Where we have one different column for each category we're interested in. We saw the data overlap, so just by eyeballing it, it's not clear to see if there's a significant difference between the two groups. So we looked at the difference. Again, this looked fairly
innocent
and fairly centered around 0. We saw on average, girls are about 1 point better. With a standard error of 0.05, then we introduced the t-statistics, which we had already seen in a similar context for linear regression, if you remember from the previous week. If you remember, there it was the coefficient in the regression model divided by the standard error of the coefficient, so a very similar formula. And we saw we got a value of 17, that is 17.6, which is highly significant, so it's very unlikely that this difference is caused by chance, although it is very small. And we saw that something similar can be, that this can be directly computed using the t-test_rel for paired samples test in the SciPy stats library, or alternatively using the one sample t-test on the differences. We saw that if we just select random normal numbers with the same standard error, it's very, sorry, actually a bit too far up. Here we are. That's very unlikely that we get such a big discrepancy of about 1 merely by chance. Okay, then we discussed how t-test makes a couple of assumptions, like normality of the, like both the distribution of girls and boys' grades around their respective means, so what we call the residuals when we talked about regression, that t-test assumes that these residuals are normally distributed, actually also assumes that they have the same variance in both groups. And we say, okay, if you want to relax this assumption and just assume that they don't have to be normal, we just want to check if they are the same for girls and boys. Then we said, under this was called a null hypothesis. So the hypothesis that there's not actually any meaningful difference between the groups. We would get girls being better than boys at about the same number of occurrences, subject to statistical fluctuations. And so we saw if you looked at a similar number of total observations, so the ones where they were different, 19,541, and just flipped a coin, we would get girls better in between 9,500 and 10,000 occasions. So anything in this range of the girls being better could be explained by chance. However, a number as high as 11,050, which would be somewhere out here again is very unlikely to be due to chance. So even under these relaxed assumptions, where we don't assume normality, we still see that this is a meaningful and statistically significant difference.
Good.
Okay.
Daniela, I see it's under the hypothesis testing course, but I see it has, even though I put it up, it has not been pushed live, so we will do that today.
So yesterday, Ilona said something which some people are saying that, okay, if you don't look just at the mean scores, but if you look maybe at the students that are particularly good in mathematics, that their boys are much overrepresented compared to girls, and consequently they are also overrepresented.
I don't know if it's mathematics. And this is we need to confirm, but I remember a discussion from a professor about having actually I think it was IQ distribution. So the argument was if both of them are roughly normally distributed, but the women's distribution is more peaked, so it
is leptokurtic.
More leptokurtic.
No, sorry, the men's distribution is leptokurtic, so it has more outliers.
Correct. Men's distribution has more outliers, so the women's one is more platypurtic. So it has a higher peak in the middle and fewer outliers at the two ends, versus the men's has a bit more outliers at the end, so that there are supposedly more
extreme
results.
Mm-hmm. Yeah. Well, okay. We cannot check right now if this is a popularly held belief. We can just check if there's any evidence for that, at least for that being the case in mathematics, at least in this particular data set. So for that, we can prepare a second pivot table, which shows just the percentages of the students in the highest category, which are considered excellent by the examining board. So that's just the same formula as we had before, but now we're taking the values of the level 4 percentage, so the percentage of students in each group in the highest category, rather than the mean score. Otherwise, it's exactly the same as we had above. So we see, okay, actually there are some groups like 2007, grade 3, district, borough 101, M015, where we have 27.3% of the girls being excellent and only 5% of the boys. There are other examples where it's the other way around, like here in 2007 for the boys, 17.6 versus 8.7. Generally, there tends to be a bit more variation among the very good students than for the mean, so it's can be expected that this is more due to subject to statistical fluctuations. However, now let's look at the histograms of both groups and see them in overlay. And again, we see something that actually looks quite different. So we have something, so most groups actually
looks quite different.
Well, so this histogram looks very different from the one we had earlier.
Yes, I thought, but the girls and the boys look really.
But the difference between girls and boys, we'll look at that later. Yes. But just so we have first, I mean, the percentages are all between 0 and 100%. Then the mode in this case is 0, so most groups don't have any excellent students. And then it sort of slowly tapers down.
Could we go one more time at what this graph is showing?
This is the percentage of students among all students in the same grade, year, gender, and
who are excellent,
and district, which are considered excellent based on their score in mathematics.
Mm-hmm.
And we see there's a huge variance here, which might be expected because New York contains very different school districts with very different socioeconomic backgrounds. So there are very, very few where basically everyone is excellent. And it's much more likely that nobody is excellent. And sort of the percentage of excellent students sort of gradually tapers off from 0 to 100%. Okay, now let's just look at again, let's do this t-test, which is in this case a little bit more dubious than that was previous, because this is definitely not a normal distribution.
Is there, will you talk about something, is there a possibility to shape distributions like this? You said sometimes it's a good idea to massage them and try to throw them into some sort of normal distributions that we could.
Sometimes, so if you have skewed distribution, there are some things you can do. It's not always possible. For instance, if you have something which is very right skewed, where you have something which is, can people see that, which looks maybe like that, which has lots of outliers on the right and then sort of tapers off, then often it's a sensible idea to take logarithms. Especially if you have data with a very, very large range, things like salaries. Something like here, between 0 and 100%, this might not be so useful here, especially logarithm of 0 is not really defined. So this is something, applying these transformations is a bit of a trick that in some situations helps, but it's not the panacea, so you can't always do it. They're just some, it's something to keep in your toolbox, but generally it's important you have to be able also to deal with non-normal distributions, because normality is unfortunately not as normal as we think it is. Quote of the day. Right, okay, now let's just blithely sort of disregard the fact that our normality assumptions here are valid, and just do the t-test as we did it before for paired samples. And we see, in this case, we see actually on average girls are also a little bit better here. So because one, positive values always mean girls are better, but this is not statistically significant anymore. So this could be explained away by chance. So p-value of 0.3. Here we actually look at the differences between females and males. We see something like that, which has a big peak in the middle and then quite steeply.
That looks very platty.
Exactly. Well, actually leptokurtic, because you have a big peak here and then you would have outliers here. So I believe if we looked at the kurtosis, I may be wrong, but
okay.
Yeah, so in this case we get something which is positive. And which is bigger actually as what we had for the mean differences, which were up here. This was, I mean, these are both leptokurtic, and this is even more leptokurtic. So generally, as a reminder, so leptokurtic means you have a lot in the middle, in the central peak. You have big outliers, and you have not so much sort of in between on the medium level, whereas otherwise you would have something that is much more gradual, which is sort of which doesn't sort of fall back, so which sort of falls off more smoothly here, but then doesn't go so far out. Okay, and again we can check. Since we don't have normality, let's use the other test that we had yesterday, where we count the number of cases where boys and girls are better. So girls are better in 9,943 cases, boys are better at 9,600 about. So that's much closer. And if we now take the sum and of the two, which will be about 20,000, a little bit less than 20,000, and do again as many coin flips, then we actually see 9,943. This is something that can happen.
Almost 2 standard deviation.
Yeah, I think. Well, we can compute that, but let's. I think it's a bit. Yeah, maybe about 2 standard deviations. So let's compute that. So FB minus X mean divided by X standard deviation, 2.5. Good point. Yeah. And so by chance, this would be seen, this would occur in about 0.7% of cases. So that's something that can happen. It can happen not extremely rarely, but generally most people would still assume that to be statistically significant. So even if we look at only students in this top group of ability, sort of the very best in mathematics, there's some weaker, in this case, still some weaker evidence that girls are better than boys. And we see that we can get this with this assumption-free test that shows that. So we get it in about 0. We would have, this is what we would call the p-value, so the probability that we could get under the null hypothesis. So if there was no difference between the two, we would get random coin flips. We would get such an extreme value in about 0.7% of cases, would generally be assumed still to be statistically significant. However, the t-test in this case did not show a significant difference. So in this case, the fact that it's not normal, these distributions are not normal, really sort of destroyed everything. It means the test is not really applicable here and will give us a wrong result.
Yeah. Any questions so far or comments? Otherwise, can I get some maybe little thumbs ups? Can we get some little thumbs ups? Awesome. All right.
Okay. Awesome. So we saw 2 different tests. So t-test is what we would call a parametric
But anyway,
test.
so what you're saying is we have this hypothesis is that male intelligence is, or because this came up in discussion, so that male intelligence is distributed with more outliers, and we checked it. Because we had this hypothesis testing, and we saw that in this specific data set, when it comes to math grades in New York, in this range, it does not seem to be the case. Yes,
I mean, we have to sort of look a bit critical here. So these data were not supposed, this test was not supposed to measure really extreme ability. It was not like Math Olympiads and something like that. And it's only in New York City. So we have to be careful about what we can conclude from this data and what not, but at least for mathematical abilities, let's say, still in the sort of normal range. We cannot really, we can really not support a statement like boys are better than in math than girls from this data set.
Okay, great.
Awesome. Okay, now we looked at grades. Let's look back at salaries, because this is something we were very interested in, right? Gender equality. So again, we look at a data set which in this case is from Seattle, which shows the average hourly rates for male and female employees in different job titles. And let's see if we can get any evidence for a gender wage gap here. Again, so we have to sort of see what can we conclude or not from this data set. This is public service employees, so there might be different factors at play than you might get in the private sector, for instance, but yeah.
Daniela says, I like the flip coin test. Right, yeah.
Exactly, yeah, and that's very, very surprisingly surprisingly powerful, actually, in how many cases you can just have this mental model of flipping a coin, because if you can sort of visualize your data generation in a way that only is down to a coin flip, let's say look at girls and boys and see which one will be better or not in this particular sample, then you can see each of these groups is like a coin flip, and this way you can come up with statistical tests that make very few assumptions, so you don't need normality and so on, and you can actually derive very powerful results from that. And I'm not sure if people have been busy writing down zeros and ones.
We had quite some results, yeah, right? Irina is smiling and nodding. Yes, yes, yes.
I'm not sure if we'll get to there today. Maybe I'll get there tomorrow, and then we can actually compare that against coin flips and see if we see anything interesting. All right, so let's look at this wages data set. So here we just look at the first 5 rows. So we see, for instance, for accountants, the average hourly rates for females is $30.58. For males, it's $30.28. In total, it's on average $30.51. And then you see the number of female, male, and total employees, and also how long everybody was in their job so far. Let's rename some of these columns just so that we don't have to type so much. So instead of job title, we just write job. Instead of female average hourly rate, we just write female rate, and so on. And only look at these 5, and we only extract these 5 columns just to make it a little bit easier to work with. So here we have a bit more of an compact data set now, where we just look at the numbers that interest us, mostly the female and the male rate, but we also want to look later at some point about the number of employees in each job.
Well, so far, actually, well, let's see what that gives.
So let's just plot this, plot some histograms to see if there's anything funny with this data. And we see, if we plot, for instance, the female number, then most job categories are very, very low around here, 0 to maybe 100, but then we get one outlier with 3,500. So this is something that looks a bit suspicious.
Can we look at the logarithm of that? Or it doesn't matter? Like there's nothing in between, basically.
Yeah, I think you mean a logarithmic y-axis, x-axis. I'm not quite sure if this can easily be done. Yeah. Well, yes, you could do the. Sorry, you could do the. I'm getting off script here, but see if this works. So here we apply the logarithm to the numbers and then plot the histogram. And then we see here, okay, this would probably be 1. So the logarithm of 1 is 0. So many jobs where there's only a single, let's say, female employee, then it's sort of, this would be 2, 3, 4, and so on. And then we get there's something, then the outlier here. And let's look at what what job actually corresponds to the biggest number of employees, and that's the grand total. So there they are all summed up. So we will remove that, and we will also drop all cases where we have missing values for either male or female employees, because of this we can't make a meaningful comparison. And then after we pre-processed our data set this way, let's look at the distribution of female rates and male rates. And again, we actually see something that doesn't look extremely far off. So just by eyeballing it, it might be a bit difficult to see. We see that there may be a huge difference between, I think the lowest jobs seem to pay around $10 per hour, and there are some jobs which are usually probably executives or lawyers and so on, doctors, where it pays more than $80 per hour. And looking at the difference between female and male rate, again, we see a very leptokurtic distribution. So in most cases, the difference in hourly wages seem to be zero, but we get some examples where women may earn almost $15 more per hour, and some where males are earning $15 more per hour. So let's again do the t-test. Again, so t-test was assumed this is normal. This is not normal, but it's closer, much closer than what we had up there when we were looking at the percentages in the highest categories. So it's a bit dodgy, but it's a bit dodgy, but not too dodgy. So I think in this case, many people would still be comfortable using a t-test. And we get this result. So there seems to be, so first, on average, women are earning a bit less than males, about $1 per hour. However, in this case, this difference does not seem to be statistically significant. And so this is when we use the t-test, it assumes normality. If we just use the coin flips, which is a more robust test, which assumes less. So there are 154 jobs where actually females are earning more, and 137 where males are earning more. You see, this is, like on average, the difference in wages is $1 more for males. But because we have such an outlier-rich distribution, we actually get slightly more and also slightly skewed distribution. Actually, we get a few jobs more where women are earning more, just a little bit, because this doesn't look at the absolute difference. And now let's do a lot of coin flips and see how often we could get something like that by chance, and this is 16%. So in this case, at least for the city of Seattle, we cannot conclude that there is evidence for a wage gap, which may make sense because in the public service, people are usually paid according to a pay scale and so on, so it's not so much room for negotiation often. Might be different in other cities. We could look at data from New York when we get them, or other countries. So a little different. So a little side note. So we see also that, well, we could say it's maybe not so meaningful because different kind of jobs. Here we just compare every job as if they count equally, right? We compare accountants where we have, let's say, 30 people in total with acting technicians where we only have one person, right? So this means, and we treat them all as if they count the same. Now, however, maybe we want to account for the fact that jobs with a lot of employees should count more than ones with very few employees. And for that, it's not an easy way how this could be done with the coin flips, but at least for the t-test, we can do a so-called weighted t-test. And in this case, which we use the stats models library, a different library, and we use the weight stats module, which allows these kind of tests with weights. And if we now compare female rate versus male rate and account for the number of different female and male numbers, we actually get a t-statistics here of minus 15.5. And we get something that does look statistically significant. Whereas up here we got a t-statistic, sorry, this was not $1 difference, it was a t-statistic of minus 0.9, that was a mistake. But here we got minus 0.9 and not significant. And here with the weightings, counting more the jobs which have actually many employees rather than just, I don't know, one female executive and so on in some category, we get something like minus 15.5, which would be considered highly significant. So this shows that if we account for weightings, if we count what sort of counts more or not, like jobs with many people in it, than just jobs with a few people in it, we might get a very different picture.
What does the t-statistic of minus 15 mean here?
Minus 15 means males earn more.
And in what sort of units, or this t-stats are squared? Or
so t-statistic is unitless. Mm-hmm. It is, I mean, so without the weights, it would be weighted, it would be mean divided by standard error.
Okay, yes.
So the difference in means divided by in units of the standard error, and in this case, it's a weighted difference in means divided by a weighted standard error.
Excellent. This really shows that if we gave up, let's say, one step before this, then we would get completely different result to our hypothesis testing. Okay? Yes.
Exactly. So in this case, it shows often it's sensible to look at different kind of statistics to get a more meaningful picture. Just to say, rather than just look at a single one. And often it's not, you can say, okay, this one is right and this is wrong. But if you report different ones, you will get a much more nuanced picture of what the situation in gender equality or anything is really than if you just give one number and assume this tells you everything.
I think this is a little bit of an issue about reporting and journalism in general. Would you agree, ladies? Is that providing a nuanced story, A, takes time, let's say on the page, and B, it does require for the audience to understand.
And for the journalist to understand.
Well, okay, yeah. I mean, the prerequisite, yes, but even if the journalist, as a professional, would have this. You are like what?
Sometimes they do. Sometimes they do, but not always.
Yeah, because those things are not black and white, and it really takes consciousness to think about these nuances, right? It's much easier to write some sort of, well, it's not only easier, I think it's usually preferred in journalism to write some sort of sensationalist headline about a single piece of, I don't know, an outlier or some.
Yes, that's
something disturbing. It's not put in context.
That's probably more a matter of psychology than statistics, so how to make people interested in different things. Okay, so I think this is our program for today. Are there any questions? Could we compare by job title without waste stats? Could you explain the question? I don't quite understand it, Irina.
Okay, so we used the second test to divide by job title and to understand the difference. But could we do it like we did before, without the weight stats? So we used two different t-stats, and I didn't understand why we should use weight stats here.
So the point of weights in this case is that jobs where there are many women or men count more when we compute the differences than just jobs which maybe only have one of each. So this means if we have a, let's say, weight difference for if let's say we have an accountant and we have 20 accountants and 1 executive. And let's say for accountant, and there are 20 accountants and just, I don't know, 2 executives, 1 man and 1 woman. And for the accountants, let's say men earn $1 more per hour, and for the executive men earns $1 less than the female executive, let's say, one example. Then we would say, if we just aggregate amongst the job titles, we would say, okay, for accountants, it's 1 more, for executives, it's 1 less, so on average, it's 0. But however, if we account for the fact there are 10 times more accountants than executives, then we would get a different picture. Then it's no longer 0, because it's then sort of 10 times +1, +1 times -1, divided by 11. So in this case, we would get a non-zero difference. Does it make sense?
One thing that I'm curious about is we dropped all the job titles where there was a missing value. So any job title where there wasn't a woman, or any job title where there wasn't a man, got dropped. I don't know how many we dropped. Like, for example, also there was an outlier. What if there are, I don't know, 3,500 janitors who are all women and they make nothing? They, I don't know, paid $8 an hour. We just dropped all of them if there wasn't a male janitor.
And all the
vice versa.
lawyers that make lots of money are men. That's true. So
we dropped those as well. And maybe it's the other way around. Maybe, there are a lot of truck drivers and they are all men and there's no women, so we dropped them. Like, how do we reconcile those?
Yes.
Or is there something we can do about that?
Yes, we can do, but I think it doesn't fit neatly in this kind of comparison here. So I would probably deal with these separately. So one thing you could do is, the nice thing in this case, by comparing like with like male accountants versus female accountants and so on, you can do the paired analysis, which means we ignore all the effects by different education, different market values, market rates, different jobs, and so on. However, there are some, if we throw away some of the effects, like why are there different people in different categories to begin with? So we could just also put all of these jobs into one big basket and then compare sort of the distribution of the rates while ignoring the job titles. So we treat everybody as if they all have the same jobs. This would be the independent sample t-test rather than the t-test which we used here as well. Sort of this would here this is something we slightly did here, right? Because by having these different weights, by accounting that we had different females and males in each category, we saw that we don't no longer have this like-for-like comparison, and I think this might be possible if one of these weights are now 0. I would have to check this, but in this case, I think we might run a similar analysis, which includes the people which we threw out. So again, that's a good point, and here I would probably do different kind of analysis. And wondering if it makes sense to explore IBM SPSS statistics. So yeah, if you want, so this is something which costs money. If you don't want to pay money, there's also specific statistics modeling language called R, which has many of the functionalities of SPSS, which I would recommend to look at if you want to do a lot of data analysis and statistics. I think you can get quite far with Python, and the normal stuff, like what people normally use, is generally available in Python. If you want to look at very exotic or research level statistical analysis, this tends to be available in R rather than Python.
Wonderful. All right, I think that's a good last word. Thank you, everybody. Screen share. Thank you. Please pat yourselves on the shoulder, and we will see you tomorrow.
See you tomorrow. Bye bye.